Bismillah ar-Rahman ar-Rahim. Welcome everyone in this video about Chapter 1 of Mechanical Vibration course. Here we start with fundamentals of vibration. Before we diving into questions and analysis, we need to understand the basics, the concept of vibration actually, what vibration actually means, why it's happening, and why we study this vibration in engineering. Okay? Vibration, simple way, it's oscillatory motion, okay, of a body around an equilibrium position. What does that mean? That means when a system moves back and forward repeatedly, like this maybe system, like a pendulum swinging or car suspension bouncing after hitting a bump, something like this. This is vibration, okay? You see vibration all around you. The movement of tall buildings during earthquake, la samah even humming noises of machines or engines. This also vibration. Okay, all of this, all vibration, all this, as engineers, we need to understand it to control them. That means, what's the importance of that? Now, why do we study vibration? We use this knowledge to control the vibration, because uncontrolled vibration can cause very, very, very serious problems, like noises, like wear, like fatigue failure in machines, and something, if it's go on the big scale, it will go cause a disaster like a bridge collapse, la samah Allah. In the other way, in the other hand, can be the vibration can be it's useful, used in medical applications like ultrasounds machines, and that means vibration can be harmful and useful. And our job, engineers, to analyze and control the vibration. Okay, now we have defined the vibration. Let's look to the basic building blocks to the any vibration system. We can break down vibration system into three fundamental parts. The elementary parts of vibration system. First, the mass. Second, the spring, and the third, the damper. Okay. The mass is represent the object that moving, provide the inertia, okay, that resists acceleration according to Newton's law, because you know the heavier mass need a bigger force to accelerate, okay. The spring provide elasticity, okay, and restore the force proportional to this displacement. When you displace the mass, the spring push it back toward the equilibrium position, okay. The damper, the third one, is like a shock absorb, okay. It resists the motion by dissiping energy, okay. And usually it's form heat, because the energy it's go, it's transformed to another energy. Usually it's a heat, okay. A perfect real-world example is the car suspension. We can imagine the car body is the mass, okay. The suspension spring absorb the pumps, and the shock absorb acts as the damper, control the oscillations together. These three elements work to keep the ride smooth and safe. So whenever we analyze a vibration problem, remember we always come back to the these three elements: the mass, spring, and damper. Okay, to analyze vibration, we need to know how many independent ways a system can move, okay? That's called degree of freedom, DOF, the short way, okay? The degree of freedom, it means the number of independent coordinates it's required to describe system motion completely, okay? In simple way, it tells us how many direction or types of motion we need to track, okay? Let's take a simple system, a basic spring, a mass system. It has just 1 degree of freedom. That means we can fully describe the motion using 1 coordinates. Okay? Complex system, like a car body, it can bounce up and down, okay, and at the same time it switches forward, or backward. That means has 2 degrees of freedom. Okay. There's also continuous system. That system, like beams, building, or strings, have infinite number of degrees of freedom. Because why it has infinite number of degrees of freedom? Because every single point, okay, every single point of it can vibrate. To study those, what we use the differential equations and approximation methods. So, degree of freedom is one of the most important concepts in vibration analysis. It tells us how complex the system and what type of equation we will need to describe this motion. Okay, now we understand the degrees of freedom. Let's look to important categories of systems: discrete system and continuous system. Okay. Discrete system has limited number of degrees of freedom that we can describe the motion with just a few coordinates. Okay, limited number of degrees of freedom. Also, systems are usually molded with lambda masses. That mean mass add together and lambda. Okay, and their behavior is described by ordinary differential equation. Okay, example of that, like suspension in the car, we can consider the body of car is 1 mass and the rest is the spring and damper. Okay, a continuous system has infinite number of degree of freedom. Okay, because its masses are distributed through the structure. That means if I have a string of vibrating guitar, the string, every point will vibrate. That means we need partial differential equation to make compare between these two systems. In real engineering problems, its continuous system are often approximated as discrete ones. Why? To make analysis easier. For example, instead of modeling every point of building, no, just we model a few floors as lambda masses. Okay, that still gives us accurate result for design and save a lot of computation time. Because it depends for your how much accuracy do you want. It depends on that, or whether we treat the system as discrete or continuous depends on the required accuracy you wanted. Okay, now let's talk about how vibration can be classified. Okay, first the peak vibration. The system vibrates to the initial distribute only, with no external force after initial displacement. That means like you pull down a pendulum and let it go. It swings back and forth on its own without any further input. That only the driving this motion, the system's own stored energy. This is the free energy. Okay, the post energy. The system responds on external excitation that may be periodic or random or shock. Like rotating machine that apply repeating force, or random, like wind, okay, and even shock, somehow like an earthquake. In force vibration, the system keep responding as long as the external force is applied. That's force vibration. Also, we have damped with undamped. In real life, all systems have damping. They lose energy through friction, resistance, so the motion gradually dies. Okay, undamped system, it's idealization. We use it in the theory, where no energy is lost and oscillations would continue forever. Also here we can classify by mathematical model and by the nature of excitation. By mathematical model, we have linear and nonlinear vibration. Okay, the linear vibration is restoring the force directly proportional to the displacement. That's is Hooke's law, F equal kx. Okay, and the nice thing about linear system is that by the superposition principle applies. That meaning if you know the response to the input separately, you can just add them to get the total response. That much easier to analyze. Non-linear vibration, the force is not proportional to the displacement. Okay, these systems are more complicated and we often need approximate method to solve it. For example, very large deflection in structure or materials that don't follow Hooke's law fall into this category, the nonlinear vibration. By excitation nature, we have deterministic, okay, also rather random. Deterministic excitation, if the external force or input predictable can be expressed with known mathematical function, it's called deterministic, okay? Example, rotating machinery. It's vibrated in periodic and predictable, okay? The random excitation, like the wind force, the earthquakes, la samah Allah, this required another methods for analysis since we cannot predict the exact input. Now let's look at how Unit actually analyze vibrations, the systemic producer we follow. Okay. First, model the system. That means we simplify the physics structure into ideal model made of mass, spring, and dampers. Okay. Determine the degree of freedom and system boundaries. All this model the system. Okay. Second, we derive the equation of motion. Okay. Applies Newton's law of energy or energy methods like Lagrangian machines. The result, one or more differential equations that describe how the system moves. Okay. Third, solve the equation. Use analysis method or simple system. Once you have a equation, we need to solve it for simple system. We can find analytic solution. For more complex system, we often use numerical method or computer simulation. Okay. For interpret the result. After resolving, we interpret the result. We look at important characteristic such as a nature frequency, the mode shares, the response amplitude. We also check for reasons, conditions, because reasons can be dangerous if not controlled. Finally, we apply the result to design and maintenance. That means making changes in the system to avoid harmful vibration or setting up monitoring protocol to ensure safety during the operation. Now let's look one of the key elements in vibration system, the spring. The spring provide restoring force that brings a system back toward equilibrium when it's displaced. Okay. Type of spring, linear, non-linear. Okay. Linear spring, the most common type of linear spring, its force directly proportional to displacement. According to Hooke's law, F equal kx, where k is spring constant. Okay. Linear spring are simple to analyze and are widely used in engineering. Non-linear, in real life, many springs behave in non-linear way. Okay. The force can include higher order terms like this equation. So these cases are more complex and often. So these cases are more complex and often require special techniques or linearization around an operating point to analyze them. For spring combinations, spring can be combined as in series, then the K equivalent it will look like this, or parallel, then the K equivalent look like this K1 plus K2. This also can be simplified like K1 multiplied by K2 over K1 plus K2. Okay, now let's look about one of the also vibration elements, the mass, or sometimes we call it inertia element. Okay, mass, it provide inertia property of a system. Okay, according to Newton's second law, F equal ma, mass resists acceleration. Okay, it also stores the kinetic energy during the vibration, and it's play direct role in determining the system nature frequency. Okay, the equivalent lambda mass models, what's mean for simple analysis. Okay, distribute the masses or often represent as a concrete lambda mass. That for simplify the study, okay, we assume like car body, single mass at center gravity, or beam can be modeled as a series of distracted masses along the net. That means because of beam, there is a lot of point that's as we said, continuous system, but we simplify it as discrete system and model it as a series of discrete masses. For complex machinery, we represent multiple concreted masses at key points of interest. Just this key point, because we need to simplify, as we say, the study or the analysis. Okay, now the third element in vibration system, the damping. Okay, the damper remove energy from the system, usually converted into heat, and play a big role in controlling vibrations. Okay, we have three types: the viscous damping. We have three types. Okay, the viscous damping, the column or dry friction damping, or also the hysteretic or material damping. Hysteretic damping or material damping. Viscous damping, it's most common type where the damping force is proportional to the velocity. F تساوي F equal CV. A real world example in automotive shock absorb. This model is widely used in vibration analysis because it's mathematically simple and effective. Column or dry friction damping. Here the damping force is constant value that always oppose motion regardless of speed. For example, friction in machine slides or bearings, unlike viscous damping, it doesn't depend on velocity. Okay. Hysteretic damping or material damping, which happens inside the material itself. Due internal friction, energy is dissipated within the material structure, and it's proportional to stress and strain. Example include rubber or polymer, and even metals when they flex repeatedly. Okay. And the damping, it's just like the spring, can be combined in series or parallel to achieve desired behavior. And it's often engineers use equivalent viscous damping. Okay, because to approximate more complex damping mechanism. Now let's look at the most fundamental form of vibration, harmonic motion. This building block for understanding all other kind of vibration. Harmonic motion described by this equation: x t equal x sine omega t plus alpha. Here, what's each term means? X, what's X? Amplitude. The maximum displacement for equilibrium. Okay. The omega, it's the angular frequency measured in radians per second. The F, the ordinary frequency measured in hertz. Okay. The T is the period, the time to complete one full cycle. Okay. And the alpha, the phase angle, would shift the motion in time and can be given in radians or degree. Okay. Even though many real-world vibrations are complex, we can break them down into some harmonic motion. That's why harmonic motion is important. It acts as the foundation for analyzing more completed vibration. When we study a vibration system, we always return to the fundamental sine wave behavior because it allows us to build up and understand any complex motion step by step. Now, how we represent a harmonic motion. There is two other useful way to represent it. The vector or phasor method and the complex number for, okay? First, the vector. Imagine harmonic motion as the projection of rotating vector or phasor on the vertical axis. The length of the vector is the amplitude. The angular velocity is of rotation is the frequency, and the initial angle corresponds to the phase alpha. Okay, so at the vector rotates, its projection give the sine wave we see in harmonic motion. This is very intuitive geometric way to represent vibration. Okay, then we have the complex number form. We can also written the harmonic motion in complex form like this. Okay, what's the advantage of it? It simplifies the mathematical operation. It's make differential and integration much easier, and also it's help us analyze system with multiple oscillation more efficiently. And we always take the real part of the expression since the correspondings to the physics motion. So whether we use the vector, phasor, or complex number, both methods make it easier for us to handle harmonic motion in analysis. So now that we understand harmonic motion, let us see how different harmonic motion can combine. This is very important in vibration analysis because most real-world vibration are made up with multiple signals. Now, when two harmonic motion with the same frequency, but possible different phases combine, we can express as like this. But for simplify to deal with this equation, we can here see this the new amplitude and this sign the new phase of angle. Okay, mathematically we can calculate them like this. We convert this to this and this. Why? Instead of dealing with two separate sine function, we reduce everything to one equivalent sine function with a new amplitude and phase. This process become much easier if we use complex notation with complex number addition of harmonic motions and just vector addition in the complex plan. That's why engineering prefer phasor or complex form. They greatly simplify vibration analysis. Most vibrations are more complex. That's where harmonic analysis comes in. According to the Fourier series, any periodic function can be expressed as a sum of simple sinusoids. Okay? That means even a complicated vibration can be broken down into many simple of harmonic motions, each with its own amplitude and frequency. Time domain versus the frequency domain. Here we can look at vibrations in two different ways. The time domain, we plot amplitude versus the time, which shows how the vibration change over the time. But in the frequency domain, we plot amplitude versus the frequency. which tell us which frequencies are present in the vibration. We move between two domains using the Fourier transform. Why it's matter? Because it's useful for engineers, because it's help identify the problematic frequency in machines or structure. For example, if machine vibrates strongly at the natural frequency, harmonic analysis will reveal the peak clearly in the frequency spectrum. Okay, now let's wrap up this chapter with a quick summary for the key concept we have learned. Okay, first, the core concepts. First, vibration is simply oscillatory motion around equilibrium. Okay, every vibration system can broke down into three elements. We said the massive ring and damper elements. The number of degree of freedom determine how complex the analysis will be, and the vibration themselves can be classified as free or forced or damped or undamped or linear or non-linear. Okay. Second, the analysis techniques. We saw that the vibration analysis follow a systematic producer, model the system, drive the equation, solve them, interpret result, and then apply to design and maintenance. We also learned the harmonic motion and the foundation of understanding vibration. We also using complex representation. Also using complex representations make the math much easier. And with the Fourier analysis, we can break down complex signals into harmonic components for easier study. Finally, why is this important? Because understanding vibration is essentially an engineering practice. It allows to analyze, predict, and control vibration in a system. From car suspension to aircraft wings to buildings, control vibration prevent failures, improve safety, and optimizing performance. And thank you for your listening. If you have any questions, let me know down in the comments.